All right, welcome back. Dr. P here, and in this lecture we're going to look at molecular orbital theory and how it applies to explaining how cycloadditions work. Now I should note that I'm doing these topics in a little bit different order than the text does, but I figure since we've already talked about the Diels-Alder reaction, then talking about cycloadditions first when we talk about molecular orbital theory is kind of a natural thing to do. So remember, we need orbital overlap to get our reaction. So if we have our diene, and then we have our dienophile, we need to get, I just realized I think my pen just ran out here. Let me grab a new pen. We need to get that overlap in order for the reaction to occur. So let's look at the molecular orbitals. So first we will look at the diene. So we'll put energy, our axis there. This is going to be our diene. And since our diene has 1, 2, 3, 4 p orbitals, we're going to get 4 molecular orbitals. 1, 2, 3, 4. They should be equally spaced. If not, I apologize for not drawing things as equal as they should be. So I'll have 4 p orbitals. It does get a little bit repetitious, drawing all of these in. Now in reality, the molecular orbitals don't look like individual p orbitals. They are the p orbitals added and subtracted in different ways. So at our lowest energy level, all of our p orbitals are in the same phase. You may remember this from a chapter 14 lecture video talking about the stability of conjugated dienes. So that's pi 1. Now I've got 3 other molecular orbitals here, pi 2, pi 3 star, and pi 4 star. And as I go along, I start introducing nodes. That is a place of 0 electron density where the phase of the orbitals changes. So I have one node for pi 2, and now for pi 3 star I'll have 2 nodes. Oops, sorry about that. There we go, that's a little better. And then pi 4 star I'll have 4 nodes. I think I may have colored these in with like red and blue before, but I'm just doing the shaded and not shaded. Now when I put my electrons in, and in this case I think I'll use a different color, I'm going to, actually no, I'll just keep it black and white for now. I've got 1, 2, 3, 4 pi electrons. That's in my diene. Now my dienophile over here, again I'm going to have energy, and then I'm going to have just 2 levels because I only have 2 pi bonds. And so one of them has no nodes and one of them has one node. So I have pi 1 and pi 2 star. And then I've got 2 electrons and they're in the pi 1 orbital. So the way that these pericyclic reactions work, the way that the Diels-Alder reaction works, is that we need to get overlap of the correct molecular orbitals from the diene and the dienophile. And so we need to get good overlap and it has to be between the highest occupied molecular orbital, or HOMO, of the diene and the lowest unoccupied molecular orbital, or LUMO, of the dienophile. So we need to get good overlap between, we'll just say between highest occupied molecular orbital, HOMO, of diene and lowest unoccupied MO, or the LUMO, of dienophile. Okay. So I can take a look at this and I can say, all right, here's my HOMO, so highest occupied molecular orbital of my diene. And so what that is going to look like now is, if I draw it like I drew this guy here, I'm going to color these in, and I've got that's shaded and that's shaded. My node is right there, so then the bottom ones are shaded over here. And if I look at my LUMO of my dienophile, I see that I've got one end is shaded, and the other end I've got the opposite phase. So what do I have? Well, I end up with, we'll do blue here, I end up with that good overlap here. So same phase. And then same thing over here, same phase. So I get good overlap. So it's not just that we have overlap of the orbitals, but rather the phases of the orbitals are the same. And what this is called is frontier molecular orbital theory. And what frontier molecular orbital theory states is that you don't have to worry about orbitals that are lower in energy than the highest occupied molecular orbital, or orbitals that might be higher in energy than the lowest unoccupied molecular orbital. Of course, we don't have those in the dienophile because there's only a HOMO and a LUMO. But we're just interested in these particular orbitals. Not pi 4 star, not pi 1 of the diene, etc. Okay, now we can use this to explain, so this explains why the Diels-Alder reaction works. We can use this to explain the other cycloadditions. So this is our Diels-Alder reaction. Let me just make a note of that here somewhere. So we'll say for DA reaction. The Diels-Alder reaction is an example of a 4+2 cycloaddition. I think I mentioned that when I introduced the Diels-Alder reaction. But that means we have 4 pi electrons on one component and 2 in the other. Now, we can look at a 2+2 cycloaddition. And remember what I said before in lecture 1 is that this reaction is photochemically allowed but thermally forbidden. So let's see why that might be. So we'll look at our MO diagrams here. Alright, so we'll have one alkene, and we'll have our pi and our pi 2 star like we did before, and then we will have another alkene here, with our pi 1 and our pi 2 star. So I can put in my electrons, and I have, like before, I've got my HOMO, and I have my LUMO. But we can see here that the HOMO and the LUMO, if I look at my orbitals here, I have some good overlap, but then I have an area where I have opposite phases, which is poor overlap. Okay, so that is bad. So this is why this reaction will not occur. And we say it's thermally forbidden. So we have to do something else. So what we're going to do is we're actually going to promote one of those electrons by irradiating with some UV light. So I'll shine in some UV light, it'll promote one of the electrons. So this guy's going to leave and it'll end up there. And now I have a new HOMO. That is my HOMO star. Of course, star stands for our excited state. Now I look at my overlap between my HOMO star and my LUMO. My LUMO, I've got to line it up. I'm going to flip it over so it does line up. And once again, I have the same phase, so I have good orbital overlap both ends here, and I get the reaction. So my 2+2 cycloaddition is photochemically allowed. I could go back and take a look at my 4+2 cycloaddition and see that, gee, if I irradiated with light and promoted an electron up to pi 3 star, that would become my HOMO star. And now I'd be looking at the interactions of these end p orbitals, their phases, with the ends here, and they wouldn't line up. They line up on one end, you know, that guy would line up there, but that guy won't line up there. So my 4+2 cycloaddition is thermally allowed but photochemically forbidden. And we can generalize this into what are called the Woodward-Hoffmann rules. And basically, the Woodward-Hoffmann rules, developed by two chemists, Woodward and Hoffmann, refer to whether a reaction proceeds thermally or photochemically. That's determined by the phases of the frontier molecular orbitals. And if we have 4n plus 2 pi electrons total, that's going to be thermal. That is thermally allowed, photochemically forbidden. If we have 4n, and I'll put that in a parentheses here, if we have 4n pi electrons total, that's going to be photochemical. So photochemically allowed, thermally forbidden. So they're opposite. So you would figure out in your reaction, how many total pi electrons do you have? Well, I've got a 2+2 cycloaddition. 2 and 2 is 4. That's 4n. N is just some integer here. I've got a 4+2 cycloaddition. That was my Diels-Alder reaction. 4 plus 2. 4 plus 2 is 6. Well, if n equals 1, then I've got 6 total pi electrons. So the Diels-Alder should be thermal. The 2+2 cycloaddition should be photochemical. What if I had a 4+4 cycloaddition? Well, according to the Woodward-Hoffmann rules, 4 plus 4 is 8, which is 4 times 2, and n is 2. So a 4+4 cycloaddition should be photochemical, just like a 2+2 cycloaddition is. And you can go ahead and try this, and actually I'll have you on the practice quiz, and I think there are some practice problems as well, draw out the molecular orbitals for other scenarios like the 4+4 cycloaddition, a 6+2 cycloaddition, things like that. Alright, so you can use molecular orbital theory to help explain why the Diels-Alder reaction works the way it does when we have heat, and it doesn't work if we have light, but a 2+2 cycloaddition works when we have light present and not heat. All right, so in the next lecture video we'll take a look at electrocyclic reactions and look at molecular orbitals and how those apply to electrocyclic reactions. But until then, stay safe out there. Bye now.